Hi, good morning to one and all. I am KV Harish, Assistant Professor, Department of Civil Engineering, IIT Kanpur. You are watching MOOC lecture course on hydration, porosity and strength of cementitious material. Today we will see lecture 12, Portland cement based paste systems. We have already seen in the previous lecture about an introduction about Portland cement based paste system, what is the definition of that and how we define Portland cement based paste systems as. And in this lecture we will see some of the selected topics in Portland cement based paste systems. The textbook and reference materials are shown. So in this lecture the different topics that will be handled are morphology of clinker compounds, reactivity of clinker compounds and chemical reactions in Portland cement. The importance of this topic is primarily from the fact that these topics helps to understand the evolution of properties from Portland cement based paste systems to concrete level. So an overview is as follows. This lecture will provide details about the morphology of clinker compounds, their reactivity. Both are important to understand the hydration of Portland cement based paste systems. In addition, the chemical reactions are also covered. So in this lecture, Portland cement based paste systems will be denoted as PCBPS. We will be using that notation pretty much in most of the slides. So the audience, please watch very carefully. Some general information before we head on to the specific topics. Hydration of Portland cement is based on the hydration of its compounds. We have already seen in the lectures on Portland cement that we have aluminates, aluminoferrite, alite and belite as the primary compounds, and what you may have to understand is that there are some impurities in these compounds. So essentially the pure compounds are C3A, C4AF, C3S and C2S. Now the second point is to understand the physical and chemical changes. Knowledge about the chemical reactions are important, and the chemical reactions describing the hydration of these compounds have been worked out from the hydration of pure compounds. And pure compounds such as C3A, C4AF, C3S and C2S are actually different from the aluminate, aluminoferrite, alite and belite respectively, in the sense that the latter has minor impurities. So it does not substantially change the hydration behavior, but there has been reports that the hydration of pure compounds is slightly different from the hydration of impure compounds like aluminate, aluminoferrite, alite and belite respectively. So however the hydration behavior of the latter has been considered not to be substantially different from that of the former. For better understanding, the knowledge about the morphology of clinker compounds and their chemical reactions are essential. Now let us go to the first topic, which is morphology of clinker compounds. And in the first one we are discussing about tricalcium aluminate. Tricalcium aluminate, referred as C3A, has minor impurities, and the chemical formula which we have already discussed, 3CaO.Al2O3. Density of tricalcium aluminate is approximately 30 kg per meter cube. Aluminate can exist as AlO2 minus or AlO4 5 minus or Al6O16 18 minus ions in most of the cases, and in other cases there could be other forms. However, in C3A, aluminate exists primarily as Al6O16 18 minus ions. This is very important, and Al6O16 18 minus ions can also be put up as 6 numbers of AlO4 minus ions, and they are basically arranged in a tetrahedral manner with 6 sharing corners. So, the structure of aluminate ring in C3A is shown, where you can see that the violet color one refers to the aluminum ions and O refers to the oxygen ions. So, if you take one single arrangement, you see that 4 oxygen ions are connected or bonded to 1 aluminum ions, and what you also see is that there are totally 6 such arrangement, and the number of oxygen atoms here is totally 16, but you will have totally 18 ions, which means there are 2 valence ions. So, 6 will be in the outer. So, 1, 2, 3, 4, 5, 6, and 6 will be in the inner, 7, 8, 9, 10, 11, 12, and another 6 will be bonded to the aluminum ions, 13, 14, 15, 16, 17 and 18. The crystal structure of C3A can be any one of the following, and it primarily depends on the alkali contents and other impurities. Normally it could exist as cubic structure, orthorhombic structure or monoclinic structure, but in our case it will primarily exist as cubic or orthorhombic. The structure of each particle is slightly different from the basic cubic or orthorhombic, primarily because of impurities. So, the figure shows a unit cell of C3A, and at the right you see different arrangements, cell arrangements. The first set of figures give the cubic arrangement, the second set of figures give the orthorhombic arrangement, and the third set of figures give the monoclinic arrangement. And what you have to understand is the arrangement is primarily cubic or orthorhombic, usually monoclinic does not exist. And what you see in the left side is the arrangement of ions within one unit cell, and where the green color represents the calcium ions. So, you basically have 3 calcium atoms clubbed together, and surrounding that you have the aluminum and the oxygen atoms. Now, we go to the second one, which is tetracalcium aluminoferrite, and like C3A, C4AF also has minor impurities, and the chemical formula is given, and the density of tetracalcium aluminoferrite is approximately 3700 to 3900 kg per meter cube. In C4AF, calcium exists as calcium 2 plus ions, and aluminoferrite exist either as Al or FeO4 ions or FeAlO6 ions. This is very important, and AlFeO4 ion is tetrahedral in nature, and FeAlO6 ion is octahedral in nature. We will not discuss more about the crystal structure because it is still under research. All that you have to know is that the crystal structure of C4AF is orthorhombic. The third one is morphology of Alite. Again, in Alite also has minor impurities, and the chemical formula is 3CaO.SiO2, and the density approximately is 3150 kg per meter cube. In C3S, calcium exists as Ca2 plus ions, and silica exists as orthosilicate ions, and formula is SiO2 4 minus. So, SiO2 4 minus is called orthosilicate ions, very important. Morphology of C3S is described as polymorphic, which means you have different morphologies, and its structure is slightly or significantly different from the basic hexagonal or prismatic structure. So, morphology details of C3S is provided, where the orthosilicate ions is shown here, and you have the silicon atoms bonded to 4 oxygen atoms in a tetrahedral manner, and in the main structure you will not just see this You will also see the tetrahedral arrangement along with the calcium ions bonded to each other. Now the fourth one is belite. Belite also has minor impurities and chemical formula is 2CaO.SiO2 and the density is approximately 3280 kg per meter cube. And similar to C3S, here also calcium exists as Ca2 plus ions and the silica exists as orthosilicate ions. So SiO2 4 minus, and here also the morphology is described as polymorphic, which means you have different morphologies and the structure appears more or less rounded from the basic hexagonal or prismatic structure. So some morphological details of belite is given. At the left side the structural arrangement is given, in the right side you have the unit cell arrangement, and what you can see is that one silicon atom is attached to 4 oxygen atom and you also have calcium surrounding each of the orthosilicate arrangements. Now if you see a photo micrograph of the clinker compound, essentially it will look like this, where the entire figure is having some shades of grey. So if you have a closer look at it, you have the C3S or Alite, C2S or Belite, and C3S is seen as hexagonal prisms more or less, and C2S, which should also be hexagonal but the surface is slightly rounded, and the color there is substantial difference in the sense that C3S are largely dark grey to black in color and C2S is largely dark grey, little more darker than C3S. In the case of C3A and C4AF, they are lightish grey, but compared to C3A, C4AF is lighter. In this figure largely you will see hexagonal prisms mostly, primarily because C3S content is much higher compared to others. Now the next topic is reactivity of clinker compounds. Now when we talk about reactivity, we will have to revisit one of the slide which we have already seen in the previous lecture under Portland cement, where the profile of reactions along the length of the kiln is provided, and what we have seen is that the raw materials originally present as oxides gets converted to reactive compounds. Primarily the reactive compounds are called as Bogi's compounds. So what you see in this figure is primarily the formation of C4AF, Belite, C3A, Alite, and the liquid portion of the entire melt. So reactivity of clinker compounds. Reactivity of clinker compounds primarily depend upon heating temperatures used during cement production, reactivity of ions present in the compounds. So Belite and C4AF are formed at relatively lower temperatures. If you have a closer look at the previous image, what you find is that aluminoferrite, which is C4AF, and Belite are generally formed at lower temperatures compared to C3A and Alite. The reactivity of compounds in turn depend upon the extent to which the mixtures in liquid form are burnt and how they are cooled. So the burnability and cooling part is extremely important when we are discussing about reactivity of clinker compounds. As we have already seen in the previous lecture under Portland cement, rapid cooling substantially is used instead of slow cooling because it increases the reactivity of compounds. Now the second part is burnability, and burnability of clinker is defined as the ease with which free lime can be reduced to an acceptable level in the kiln. So again free lime, just to remind you that the free lime in Portland cement is limited to 0.8%, primarily because we want lime to be properly burnt in the kiln. So, burnability is characterized by 3 parameters, very important parameters from the cement production standpoint. Number 1, lime saturation factor, and it is referred as LSF. Silica ratio referred as SR, and you also have the third one, alumina ratio, and let us see the significance of these 3 factors. Now, first of all, how do you calculate these factors? Lime saturation factor is calculated by using these 2 formulas depending upon the percentage of A divided by F, or aluminate to ferrite ratio, and silica ratio is determined by using this formula, and alumina to ferrite ratio determined directly from this formula. What you see in the first set of formulas is that if A by F ratio is greater than or equal to 0.64, then LSF is given by CaO divided by 2.8 into silicon dioxide plus 1.65 into aluminum oxide plus 0.35 into iron oxide. Likewise, if A by F is lower than or equal to 0.64, then LSF is given by this formula, CaO divided by 2.8 times SiO2 plus 1.1 times Al2O3 plus 0.7 times Fe2O3. So, these formulas basically give a direct conversion of oxides to these factors LSF, SR and A by F. So, silica ratio is given by SiO2 divided by Al2O3 plus Fe2O3, and alumina to iron ratio is given by Al2O3 divided by Fe2O3. So, if you know the values of the lime saturation factor, silica ratio and alumina to iron ratio, we will get some idea about the burnability of clinker. So, what is burnability? As we already seen, it is defined as the ease with which free lime can be reduced to an acceptable level in the kiln. Now, the significance of lime saturation factor and some information about LSF is shown. Lime saturation factor at the plant level is fixed to be in the range of 0.92 to 0.98. While calculating lime saturation factor, we need to subtract 0.7 into SO3 from the calcium content of cement, and this is arising primarily from gypsum. What does it mean? If you see the formula here, we are using calcium oxide as one of the parameters to find out lime saturation factor. Remember that this calcium oxide should not be from gypsum. For this purpose, we have to subtract 0.7 into SO3, which is the molar equivalent for the calcium oxide that is present in gypsum. So, if we subtract that from the original calcium oxide, then we can find out the LSF. LSF governs ratio of A-lite to B-lite. This is very important, primarily because if at the plant level we find that a particular cement or type of cement or particular batch of cement is not giving desired properties, and if we have to adjust the chemical composition, then this A-lite to B-lite ratio becomes very important. Now, if LSF is greater than 1, that indicates that the calcium oxide is too high. Remember that it is not that we generally prefer higher calcium oxide, all the compounds should be present at optimal amounts. So, if you have higher amounts of calcium oxide, we have to adjust something else to bring this factor within the range of 0.92 to 0.98. Now the second one is silica ratio, and this has to be in the range of 2 to 3, and the importance of silica ratio is that it governs the proportion of silicate phases, a little different from what we have seen here, where LSF indicates just the calcium oxide, whether it is too high or low, whereas here it indicates the proportion of silicate phases, and SR increase indicates that the liquid proportions are generally lower, which in turn signifies that the clinker is very difficult to get burnt. The third important factor is alumina ratio A by F, and this governs primarily the aluminate to ferrite phase ratio, and this determines the quality of liquid formed at low temperature. This value is incorporated or used to determine LSF also. Now in general we should also know that under the reactivity of clinker compounds, which compound is more reactive, which compound is less reactive. So this table helps you in that. So here you find 3 columns. In the left side you have the compounds present in cement, in the middle column you have the quantities, and in the right column you have approximately the reactivity. So C3A, remember that is approximately 10% in the entire Portland cement composition, and the reactivity is explained as rapid or extremely fast. In the case of C4AF, it is approximately 8%, and the reactivity is explained as moderate, and in the case of C3S, approximately explained as moderate, and C2S approximately 18%, and reactivity is explained as slow, and gypsum approximately 6%. Remember that the percentage of gypsum is always taken in proportion with C3A. The reactivity is rapid, similar to C3A. So with this the reactivity of clinker compound gets over. We will now get on to the chemical reactions in Portland cement. So there are primarily 4 reactions that take place. So the first one, tricalcium aluminate. The hydration of C3A is dependent on the amount of sulfates primarily from gypsum present in the Portland cement based paste system. Accordingly, you have 5 different cases which exist, and each of the 5 cases are extremely important, and hence it is requested that please pay attention. Now case 1, if the sulfates are absent, which means what we are creating a situation that assume that gypsum is completely not present. So in that case, how does tricalcium aluminate behave, or what is the reaction with water? In the second case, if sufficient or optimum sulfates are present. In the third case, if sulfates are consumed before the hydration of C3A. In the fourth case, if very less sulfates are present. Remember, it is not completely absent, sulfates are not completely absent, but you have less sulfates compared to aluminates. And in the fifth case, if sulfates are present in huge quantities compared to aluminates. So these 5 cases you have 5 different reactions. So each of these reactions are extremely important, and primarily this defines the setting time of cement. So let us see the first case. If no sulfates are present, the tricalcium aluminate reacts with water. Remember that here H refers to H2O to form C4AH13, which is generally described as calcium aluminate hydrates. In addition to that, you also have another form of calcium aluminate hydrate, C2AHI, which is unstable, and hence this immediately converts to a compound called hydrogarnet. The chemical formula is C3AH6, and you have some water. Now the problem with this equation is that the hydrogarnet is an extremely hard material and the entire reaction is extremely quick. So this reaction is vigorous and happens extremely quick due to the rapid formation of hydrogarnet, and this leads to a condition called as flash set. Heat evolved at this stage is extremely high, and hence the terminology flash set comes along with it. And at a later stage, when we see about setting and hydration, we will see what happens to this flash set. In the second case, we have a situation where amounts of sulfates and gypsum are optimal. In such cases, C3A reacts with gypsum, and here gypsum is referred as 3CS bar H2, okay, plus water, a compound called ettringite or ettringite, C6A S3 bar H32. This reaction is also quick, but not that quicker compared to the previous case, and results in the formation of ettringite, and finally we have the condition called normal set. Remember that normal set is obtained only when you have sufficient or optimal sulfates. When we say normal set, the Portland cement paste typically takes 2 to 4 hours to achieve initial setting time. Now the third case is when sulfates are consumed before the hydration of C3A. So what do you mean by that? Assume that we have either sufficient sulfates, or we have less sulfates, or we have more sulfates. Whatever may be the case, if sulfates are consumed before the hydration of C3A, which means you have this reaction C3A plus gypsum plus water giving ettringite, which is taken from the previous case, and now that you have this ettringite available and C3A is also present, in such cases C3A reacts with this ettringite in the presence of water to give another compound called monosulfoaluminates, which is denoted by C4A S bar H12. This is very important when we discuss about sulfate attack. We will see that later. This reaction converts the ettringite formed to monosulfoaluminates. Usually we do not prefer this compound, and we prefer the aluminates, the hydrated aluminates, to be in the form of ettringite. The formation of monosulfoaluminates as such does not cause any deterioration, but at a later stage, if there are more sulfates or external sulfates coming from outside, then it creates a cracking in concrete, and those are primarily or popularly referred as sulfate attack, which we will deal at a later stage. Now moving on to the fourth case, if very less sulfates are present, then C3A reacts with gypsum plus water, which would have formed some ettringite. Some portion of C3A, if ettringite are available, they will form monosulfoaluminates, like what we have seen in the previous main equations, this one and this one. So those two things happen, but if very less sulfates are present, C3A reacts with monosulfoaluminates that is formed along with calcium hydroxide and water. Remember, the mere presence of calcium hydroxide is sufficient in order to trigger this reaction. So you will have C4AH13 plus C4AS bar H12, and both of them will be in the form of solid solution. Remember that this compound is again monosulfoaluminates. The difference between this and this is that this will be in the form of solid solution, this will be only in the form of hydrated solid. This reaction is quicker than the previous one and consumes monosulfoaluminates and transforms to solid solution, and many times referred as quick set. Remember that in the hydration of Portland cement based paste systems, we usually target only at normal set. We do not want flash set, we do not want quick set, and we also do not want the next case, which I will discuss right away. In the fifth case, if very high sulfates are present, tricalcium aluminate reacts with gypsum to form, in the presence of water, to form gypsum and ettringite. But remember that since substantial amount of gypsum is present, the ettringite will not be stable. So in this case, the Portland cement based system will not set at all, and it is many times referred as false set. So as I already mentioned, in Portland cement based system, we do not prefer flash set, we do not prefer quick set, we do not prefer false set, we only prefer normal set. Now coming on to the second set of hydration reactions, where tetracalcium aluminoferrite reacts with gypsum in the presence of water to form this compound, and if you carefully look into the compound, you see that instead of A, which you find in aluminates, you find AF. Okay, so this compound is similar to ettringite, except that instead of A you have AF, and you also have some aluminate ferrite hydrates. And likewise, when tetracalcium aluminoferrite reacts with ettringite in the presence of water, you get monosulfoaluminates, except that instead of A you have AF and you have iron aluminate hydrate. C4AF forms hydration products similar to C3A, but the reactions are relatively slower. This is extremely important of the presence of iron. The presence of F in these equations helps a lot to reduce the rate of reactivity. In this slide, we see the hydration of tricalcium silicate and hydration of dicalcium silicate together. The chemical reactions are as follows. Tricalcium silicate reacts with water to form calcium silicate hydrate gel, which is many times referred to as Tauber-Morite gel or CSH gel, and you also have calcium hydroxide, which is many times called as Portlandite. Likewise, C2S reacts with water and form the same compound, Tauber-Morite gel and calcium hydroxide, but there is a difference between the hydration of C3S and C2S. In the case of hydration of C3S, the amount of calcium silicate hydrate gel formed is much lower compared to the calcium silicate hydrate gel formed from the hydration of C2S. So here in this case, if you take 100 grams of C3S, 24 grams of water, you result in 75 grams of CSH gel and 49 grams of calcium hydroxide, whereas in C2S 100 grams plus 24 grams gives 99 grams, which is much higher than 75 grams, plus 22 grams, which is much lower than 49 grams. So in summary, we have seen the morphology of clinker compounds, the reactivity and burnability, and the importance of reactivity and burnability of clinker, and some of the most famous reactions, chemical reactions in Portland cement. With this lecture gets completed. Thank you.